Hello everyone, I am Mohammad Faizan Qureshi, PhD candidate at University of Toronto. The research presented here was done as part of a comprehensive climate change project studied to evaluate effective bond length of FRP sheets bonded to concrete. The project was done under the supervision of Professor Shamim Ahmed Sheikh. This slide shows the overall experimental program for the current study. A comprehensive study was designed to evaluate the effects of climate change. This study was comprised of material tests, FRP2 concrete bond tests, small-scale and full-scale FRP rep specimens. This paper presents the results of effective bond length study, highlighted as red in the figure. The results of this base study were used to design bond test program, which included temperature variation to represent climate change effect. As per Canadian Infrastructure Report 2019, about 12% bridges in Canada are in poor or very poor condition, as illustrated by the pie chart on the right. These structures need immediate attention. Several structural strengthening techniques are available to retrofit damaged infrastructure, such as sectional enlargement, steel plate bonding, FRP sheets, etc. Among these, FRP offers better performance due to its lightweight and non-corrosive nature. It is also preferred due to its high strength to weight ratio and ease of application. It can be applied without disrupting the bridge traffic. Figure on the right shows a CFRP reinforced bridge girder. However, premature debonding of FRP sheets is still an issue. For proper retrofit design, FRP2 concrete bond properties are needed. An experimental program was designed to evaluate the bond between FRP and concrete. 3 bond properties were studied: effective bond length, bond stress, and slip. 2 types of FRP with variable bond lengths were used. The bond lengths were selected using the available FRP standards and codes. Table presents the effective bond length values calculated from available FRP codes. For GFRP sheets, all codes seem to predict reasonable effective bond length values, highlighted in green to show the range of values. On the other hand, for CFRP, a huge range was observed from 31 mm to 133 mm. This was due to different relation between FRP stiffness and effective bond length defined by different codes. ACI and CSCE code equations showed a decrease in effective bond length with FRP stiffness. These equations are shaded in the table. However, other code equations predict longer effective bond length for a higher FRP stiffness. The reason for this disagreement between codes is small dataset on which these relations were derived. This relation will be assessed in this study by comparing experimental test results, literature data, and available FRP codes. Bond specimens were constructed in 5 simple steps as shown on the slide. In first step, the concrete prisms with centrally located rebars were casted using a wooden formwork. After curing for at least 28 days, specimens were cut into 2 halves using diamond plate wet saw, as shown in step 2. In step 3, specimens were aligned using a wooden frame, and surface preparation was done using an abrasive tool. The wooden frame was then sealed using silicone to avoid epoxy penetration, and tape was applied at the unbonded region to break bond between FRP and concrete. Lastly, markings were made and FRP sheets were applied as shown in step 5. Figures on the current slide shows longitudinal and cross-sectional view of the specimen. 2 concrete prisms with protruding rebars from both ends were joined using 2 FRP sheets. Bonded and unbonded regions were provided on each concrete block. Unbonded region was provided to avoid stress concentration effects. The specimen was loaded using the protruded rebars, which was then transferred to FRP sheets through concrete. A tensile force was generated on the FRP sheet at saw cut location due to this load, shown as loaded and in the figure. Each specimen was instrumented with 2 LVDTs and strain gauges spaced at 15 mm on the tested side. 2 clamps were used on the uninstrumented side to avoid failure. All bond specimens debonded by shearing of the concrete, as shown in the left figure. Despite the unbonded region, a wedge failure was also observed at the loaded end due to stress concentration. 3 bond properties were focused in this research study: effective bond length, bond stress, and slip. Current slide discusses procedure used to measure effective bond length. Applied load generated forces in the concrete, which were transferred to FRP sheets through shear stresses in an active bond length region, which is also part of the total bond length. This active bond length region increases with the applied load until the debonding load. Figure on the right shows this variation of active bond length at various load levels. This active bond length corresponding to debonding load is termed as effective bond length. It is a distance in which peak strain of FRP sheet drops to almost zero and was measured using strain gauge values. Second degree polynomial variation was assumed in the strain values for calculating this bond length. Average bond stress was obtained by dividing ultimate load to a product of FRP width and 2 times the bonded length, as shown by equation 1. Calculated average bond stress increased with FRP stiffness for same bonded length specimens. Slip was recorded as the third bond property. Figure on the bottom of the slide shows the 3 components of the total slip. Delta P, which is the bond slip between bonded FRP sheet and concrete. Delta C, deformation of concrete due to applied load. And delta FRP is the elongation of debonded FRP sheet. LVDTs measured all 3 components. However, integration of strain values along bonded length gave us the bond slip and FRP elongation as shown by equation 3. Equation 4 shows the bond slip only along the bonded length, neglecting concrete elongation. Bond slip was used for slip comparison in this study. Test results showed similar values for both types of FRP. This figure demonstrates the effect of bond length. Significant effect on the total slip was observed. Longer bond length specimens showed higher total slip, mainly due to elastic elongation of the debonded FRP sheet. This plot compares effect of FRP sheet types on bond specimens with same bond length. Higher bond strength and lower total slip was calculated for CFRP compared to GFRP. Higher total slip in GFRP bonded length specimens was due to its greater deformation capacity. This slide illustrates effective bond length versus stiffness plot. The plot includes current test results, literature data, and curves based on available FRP codes and standards. All code equations seems to predict correct effective bond length for a few data points, but not all. It is important to mention that the CS effective bond length equation was quite inaccurate, especially for the CFRP sheets. Using the current test data and data gathered from literature with surface preparation, an effective bond length equation is proposed. Based on the research study, it was concluded that effective bond length increased with FRP sheet stiffness. Stiffer FRP sheets showed higher bond stress for same bond length. Similar bond slip values were calculated regardless of the FRP type. However, total slip was greater for longer bond length due to elastic elongation of the FRP. An analytical model was also presented to predict effective bond length. The proposed equation can predict the effective bond length reasonably well. Financial support from National Research Council of Canada and material support from Fife and Different Concrete are greatly acknowledged. Thank you.